In this video, we will be talking about photodiode. Photodiode. Now, to be precise at this point, the junction diodes which conduct when charge carriers are generated by photons. Such kind of junctions, such kinds of PN junctions, we call them as optoelectronic devices. Optoelectronic devices. So the point is that we allow the photons, we allow the light to fall on the junction of a PN junction, and there is generation of charge carriers, and this leads to optoelectronic junction devices. Now, these junction devices, I mean, if I have to introduce you with this, they conduct when electric field is applied across the junction of the diode. And junction diodes can also conduct when charge carriers are generated by exposing the junction diode to light of some suitable frequency. So it should overcome the fundamental frequency that's required to eject the electron. So we have various types of optoelectronic junction devices, and in this video we'll be talking about the photodiode. This photodiode is it's a reverse biased. It's a reverse biased PN junction, right? It's a reverse biased PN junction. So this diode is having a transparent window in which reverse current varies linearly with the light flux when it's illuminated by light. Now, in this case, certainly we have to keep in mind the reverse bias. In this case, the reverse bias it's kept below the breakdown voltage, as we understand from the reverse characteristics of a PN junction. And in principle, the conductivity of this photodiode changes with the absorption of light around its depletion layer. So this becomes the basis for this photodiode. Now, if I have to symbolize this photodiode, we have a PN junction, okay, and in this case we allow the light to fall on it. So this is my P side and this is my N side. And if I have to measure its, if I have to see the relation between voltage and current, I would like to draw this. Okay, we have a photodiode. It has to be in reverse biasing mode, so certainly this should be negative. And here we have a resistance, and then here we have a micro ammeter, and then we get it back to the N side of this photodiode. So the right thing is to show something like this, which confirms the fact that the properties of this PN junction are exploited by allowing the light to fall on it, right? So what we do here is that we use we just bias, we reverse bias a PN junction diode, we enclose it in some kind of plastic paper, and then light is allowed to fall on the surface of this plastic facing this PN junction, facing this diode. Now all other faces of the plastic may be enclosed in a metallic case. So this is my symbolic presentation of a photodiode, and then this is how to characterize the VI characteristics of this photodiode. Now, in order to understand the voltage current characteristics of this photodiode, what happens is when the light falls, okay, light has energy, and that energy, according to Max Planck, is h nu, right? So h is the Planck's constant, and nu is the frequency of the light. This is the frequency of incident light, right? So so when the light energy, when this light energy having energy more than that of energy gap, so certainly we are having a gap here, right? We have a gap, and we have to overcome that gap, right? So what happens when the light of energy more than this energy gap of the semiconductor falls on the photodiode, suppose we have electron here, this will be excited to the conduction band. So this electron will be excited to the conduction band. It will leave a hole in the valence band. So we have the formation of electron hole pairs here, right? But what's the condition that this E should be greater than that of EG? So certainly the PN junction has to be designed in such a way that it can be inducted by virtue of suitable energy that's available for the formation of electron hole pairs. Right now, this is what I'm again trying to say is this photodiode is fabricated with the consideration that the electron hole pairs are formed near the depletion layer. So if I go back to the PN junction, this depletion layer is my energy gap, and when I use the light to fall on this junction, I have to make sure that this junction responds to the energy of the incident photons that are falling on it. So what happens after this is what happens after this is these electrons and holes, they are separated, they are formed in pairs near this depletion layer. All right, so so the electric field. Now we can think in terms of electric field. What is the electric field here? I mean, the electric field makes these electrons that we have. The electric field makes these electrons to diffuse through the junction to reach N-type, and you have automatically development of holes in the P region. Hence an EMF is developed across this junction. Now, when we have an external resistor or L connected across the photodiode, right, the current IS, what we call as saturation current. Saturation current. So the saturation current flows in addition to the dark current. Now we have the dark current here. Dark doesn't mean dark. Dark current, I mean the electron hole pairs are formed proportional to the incident light or the number of photons. Thus, thus the electric current Is is proportional to the intensity of light, and the light that's falling, the intensity of light. uh, Hence, the total reverse current in the circuit can be thought as, so since we have a reverse biased PN junction, we have saturation current by virtue of reverse biasing of this PN junction. In addition of that, we are generating electron hole pairs, and these electron hole pairs are diffused. You have electrons going into the N region, you are developing holes from the other side, right? So what's happening to the overall current here is we have two currents. One is the saturation current, and the other one is the 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 dark current, right? So this dark current is IO. So the current that will be there, so you will have an additional current, so that will be I naught plus Is. So we can immediately think of having having some kind of sensing that these photons, when fall on this photodiode, there is a sensing that additionally develops in this reverse biased PN junction. So that sensing is exploited in the form of its applications. So the total reverse current, if I will plot its, if I will make a rough estimate of the plot, so how would it look like is you have the negative, you have the reverse voltage, and we have say this is my plot for I naught, and I naught refers to dark current, and this is I. Okay, so we can see here we have the this is my reverse voltage. Okay, this is my reverse voltage, and this is my photo current. This is my photo, in fact, diode current. Okay, and this, since it's in reverse biasing mode, we have microamperes. So we have to make sure that we operate this photodiode in a region before the breakdown voltage, right? So being in that state, we exploit the light falling on the junction of this photodiode, and we are able to measure a current which is the summation of the two currents. So we are finding a change in the output. We are finding a change in the resistance. Now, you can see here in the reverse voltage characteristics, we see that the variation of photodiode current with the variation of reverse voltage, as we call it, as volt ampere characteristics of photodiode. Now the volt ampere characteristics are here, and we see how this photodiode is behaving when we allow the light of suitable frequency to fall on its junction. Now these photodiodes, they have many applications. I mean, they can be used as photo detectors. I mean, they can detect the intensity of the radiation or light. Okay, so here as a sensing device, and they can be used. They are used as light operated switches, right? So the switching kind of thing, we have photodiodes, right? So they are operated by making use of this light. So introducing the light of suitable frequency, the switch can work. And then another application would be, they are used for optical communication, no doubt about that. They are used for optical communication. And the next important application is they are used in logic circuits, right? And we understand logic circuits, the circuits that work on binary numbers, zeros and ones, and 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 uh, and there are many more applications of these photodiodes. So with this, I would like to end this conversation.